So this question comes from a random person on Facebook, and they're having trouble. They want to prove that the coproduct of, well, they were initially thinking for sets, but we're going to do this in a purely categorical fashion using the abstract nonsense definition. They want to prove the associativity of the coproduct. So the coproduct of A and B with C is isomorphic to the coproduct of A with the coproduct of B and C. So obviously we're assuming we're at least in some category where coproducts exist. Of course, in sets, this is just the same as proving that A union B union C is A union B union C. So I'm going to start off by making a big diagram to keep track of all the different objects we have floating around here. So first I've got A coproduct with B coproduct, B coproduct with C, and that has the, that comes with its standard inclusion maps. And at the same time, I'm trying to show that that's isomorphic to A coproduct with B coproduct C. So that's going to come with some inclusion products. And then, of course, inclusion maps. And of course, C includes in B coproduct C. A is going to include in A coproduct B, which gets an inclusion map here. And then we also have B going both ways here. Okay, and we want to try and just do this with arrows, get an abstract nonsense proof of this fact. So the first thing we're going to do is we look at the diagram. Let me make some bit more room here. So we're going to look at the diagram B coproduct C. And over here, I'm just going to have C. And up above, I'm going to have A coproduct B coproduct C. So we just have, in this coproduct, we have a natural inclusion map from C up there. Okay, so here we have B. We get a natural inclusion map from B into B coproduct C. But then also B includes naturally in A coproduct B, and that includes up here. So then by the property of by the definition of coproduct, categorical definition, there exists a unique map F making this diagram commute. So I'm going to draw that map F into our master map here. Okay, and then for the next step of this, what I'm going to do is now I've got A coproduct B coproduct C. And now, so of course, A and B coproduct C naturally include here. And then up above, I have A coproduct B coproduct C. And now F gives me a map from B coproduct C to this thing up above. And then A, of course, that naturally includes into A coproduct B, and A coproduct B naturally includes into this thing up above. So now I have a unique map. Maybe I'll use a different color for this one. Now I have a unique map G going between these two things. So now I have this map G in my master map coming down. So since this is a unique map, all I need is a map going in the opposite direction. And if those two maps are unique, then they've got to compose to the identity map, because I always have to have the identity morphism. And so we get this isomorphism. So I'm just going to repeat this process again, but now step by step, I'm just going to replace some of the pieces here, right? So here I started off with B union C, but now I'm just going to play the copycat game. So I'm going to put A coproduct B here, where I have my natural inclusion from A here, and now this time I'm dealing with A coproduct B coproduct C. So there's a natural inclusion going up to there. And then here I have B, and then B just naturally includes to B coproduct C, and that naturally includes into this thing up above. So I get this unique map H, making that diagram commute. So in our master diagram, I now have a map going from here to here. And then playing this same game once again, and yeah, I'm just gonna like copycat this diagram, but switching things around. So I've got A coproduct, B coproduct, C is gonna be up top, and then in the middle here I've got A coproduct B, coproduct C. And yeah, so of course I have, C is just going to include in here. A coproduct B is just going to include in here. Now I just constructed H, which goes between these two. And then again, C naturally includes in B coproduct C, and that naturally includes into the thing up above. And so finally I have, let's pick a new color here, maybe orange. Finally, I have a unique map going up here. And I don't know, we call this map K. So in our master diagram, that is a unique map going up here, K. And then that finishes the proof, right? Because now I have two unique maps making everything commute going between these two diagrams. So the thing at the top and the thing at the bottom must be isomorphic.